Yeah. In the previous class, we have discussed about the real gases and ideal gases. The real gases are the gases which do not obey gas laws at all temperatures. And ideal gases are the gases which obey, which follow the gas laws at all temperature ranges. Right, ma'am? So like that, they are real gases and ideal gases. And ideal gas equation already we have discussed. What is the ideal gas equation? PV is equal to nRT is ideal gas equation. The same way, the real gases also will be having a particular equation that is called real gas equation. We have already discussed about the compressibility factor Z value. Z is equal to what? PV by nRT. Okay. So yesterday's continuation. You see, causes of deviations of real gases from ideal gas behavior. We have discussed in the previous class that the real gases deviate from ideal behavior. Real gases will deviate from ideal behavior. Okay. So why the real gases deviate? Why the real gases deviate from ideal gas behavior? That's what they ask here. They are going to give. So causes, the reasons of deviation. The reasons of deviation of real gases from ideal gas behavior. See, the ideal gas laws means what Boyle's law, Charles law, all those. The ideal gas laws can be derived from the kinetic theory of gases. KMT we studied now. From KMT, kinetic molecular theory, one equation is there now, 1 by 3 mnc square. PV is equal to PV is equal to what now here? What here? 1 by 3 m n c square. This is kinetic gas equation, kinetic molecular equation. Okay. So here kinetic theory of gases. From these postulates, we can derive what? All gas laws, Boyle's law, Charles law, all these can be derived. So this is based on that KMT, which means what here? KMT. KMT is based on the following two important assumptions. Okay. So the two important assumptions of KMT. KMT means what? Kinetic molecular theory. So KMT is based on what? The following two important assumptions. So according to KMT, the volume occupied by the molecule. So every molecule will be having what? A spherical shape. What is the volume of molecule? Volume of molecule is equal to 4 by 3 pi r cube. So it is the radius of the molecule. So it is r, radius of the molecule. So 4 by 3 pi r cube is what now here? Volume of the given molecule. So each molecule is very small in size. Very small in size means what will be volume? Very small volume. That is negligible volume for each molecule. So the volume occupied by the molecules is negligible, neglected, can be neglected. In comparison to what? In comparison to the total volume of gas. So volume of gas, volume of total gas and volume of molecule, which will be very less. Volume of molecule is very less than what? Volume of gas. The total volume of gas and total volume of gas molecule if you take. So gas molecule volume will be very less in comparison to what? Volume of the total gas. Total volume of the gas. That's what is first assumption. Actually, this is called wrong assumption. What we have to say? The important two wrong assumptions of what? KMT. According to KMT, the volume of gas molecule we can neglect in comparison to what? Volume of the gas. Actually, according to modern concept, this is wrong assumption. According to modern concept, this assumption is wrong. But this assumption is according to which theory? Kinetic molecular theory of gases. That point keep in mind. We'll discuss about this later. So we are discussing that the important assumption of KMT is what? The volume occupied by the molecules is negligible in comparison to what? Total volume of the gas. If you take one volume here, suppose if you take this one, it is what now here? Container. In this some gas is there. In this gas is there. Now in this cube, what is the volume here? Volume of the cube is what now here? L cube na? L cube is what? Volume. Okay, the volume of this total gas is L cube here. And if you take a single molecule, what is the volume of single molecule? 4 by 3. 4 by 3 pi r cube. 4 by 3 pi r cube is what? Volume of the gas molecule. So this gas molecule volume is very less in comparison to this total volume of the gas. That's what they are saying. First assumption here. Okay. But according to modern concept, should we neglect this one? Should we neglect the volume of this gas molecule? No, we should not neglect. Is that clear, ma? So it's about what now here important area to understand is. So next one. So next important thing is that now second assumption we go for. The second assumption is that, okay, the second assumption, the molecules exert no forces of attraction. The molecules exert no force of attraction. The molecules exert no force of attraction upon each other, upon one another. That means what now here, between one molecule and other molecule, no attractive force. No attractive force. So there is no attractive force between what now here? No attractive forces between gas molecules. That's what, according to what? Kinetic molecular theory. But according to modern concept, what? According to modern concept, we cannot neglect the attractive forces between the gas molecules. But according to kinetic molecular theory concept, the assumption is what? Between two gas molecules in a gas, there is no force of attraction. Okay, so the molecules exert no force of attraction. There is no force of attraction on one another. It is because neither of these assumptions, means what now? First assumption, second assumption, because neither of these assumptions can be regarded as applicable. Okay, it is because neither of these assumptions can be regarded as applicable to real gases, that the latter means what? Real gases here. Okay, so here former and latter, meaning what here? In the sentence, whatever is mentioned first is called former, whatever is mentioned second is called latter. Okay, so here according to ideal gas, in ideal gas there is no attractive force. Remember, in ideal gas there is no attraction between gas molecules. But in real gas, in the real gases there will be attractions. In the real gases between the molecules there will be attractive forces. Remember, but in ideal gases there are no forces of attraction between the gas molecules. So the latter means what? The real gases show deviation. Departure meaning what here? Deviation. So the real gases show departure from the ideal behavior. The real gases show what? Departure. They deviate from the ideal gas behavior. Why they are deviating? In real gases, between the gas molecules, there are attractive forces. There are force of attractions. Force of attraction is there. Force of attraction is there between gas molecules in case of what? Real gases. But in ideal gas, in case of ideal gas, it is ideal gas you take. So kinetic molecular theory explains about what? Ideal gas only. Kinetic molecular theory explains about ideal gases. So in case of ideal gas, there are no forces of attraction between gas molecules. But in real gases, like hydrogen, CO2, O2, all the gases what we know are real gases. So in real gases, between the gas molecules, the forces of attraction will be there. That's why the real gases will deviate from ideal gas behavior. That point mainly we have to understand. Now see here. So the scientist name is Van der Waals. Like this here, right? Van der Waals. Okay, so Van der Waals. Apostrophe should be after S, remember, not after L. Not after L. So Van der Waals is scientist name. Up to S is scientist name only. So Van der Waals, apostrophe will be after S here. So Van der Waals equation. This Van der Waals equation is also called real gas equation. Sorry, real gas equation. Okay, ma. So Van der Waals equation. So V and Van, the other Van der Waals equation. So Van der Waals equation is nothing but a real gas equation. That means what? This Van der Waals equation will give information about what? Real gases, but not ideal gases. Next, so Van der Waals equation is also called what I said? A real gas equation. Okay, ma. Now see, first point we have to understand about this is that to certify the errors means what? Now mistakes caused by ignoring the intermolecular forces of attraction and the volume occupied by the molecules. According to KMD, what we neglected, ma? What we ignored? What we ignored in KMT theory, in account of KMT, we neglected what? The attractive forces between the gas molecules we neglected, and also the volume occupied by the molecules. The volume occupied by the molecules also we neglected in case of KMT. Okay, to rectify means what? To adjust means what? No, to correct. To rectify means to correct the errors, to correct the mistakes caused by the errors caused by ignoring the intermolecular forces of attraction and also the volume occupied by the gas molecules. Van der Waals, is scientist name. Van der Waals in 1873 modified means changed the ideal gas equation. He has changed, modified ideal gas equation. So already we know ideal gas equation. What is ideal gas equation? PV is equal to nRT is ideal gas equation. So this ideal gas equation was modified by Van der Waals by introducing two corrections. Van der Waals introduced how many corrections in the real gases? To explain the real gases, two corrections. What are they? Volume correction and pressure correction. Volume correction and pressure correction. Now suppose you take here ideal gas and real gas. Real gas is in one container, ideal gas is also in same container. In ideal gas, we have taken in a container of V volume. Here also we have taken real gas in a container of V volume. Same volume we have taken. So same gas we have, same quantity of gas we have taken in two equal volume containers, real gas and ideal gas. In this, gas molecules are there. In this also, gas molecules are there. Okay, now between ideal gas molecules, attractive forces there are not. No forces of attraction, right now? No force of attraction between gas molecules. But here there are forces of attraction. There are forces of attraction between gas molecules and real gases, remember. But in ideal gases, between the gas molecules, no forces of attraction. Now see here, when there are no forces here, when there are no forces of attraction between two gas molecules, no force here, that's why these molecules move fast and collide the walls. These molecules will move what? Very fast and collide with what? Walls, and exert what? More pressure here. So exert what? More pressure. Why they exert more pressure here? Because there are no attractive forces now between this gas molecule and this gas molecule. The attractive force is negligible. Attractive force not there. That's why one molecule is not pulling the other molecule. One molecule is not attracted towards the other molecule. That is why the gas molecules move very faster in ideal gases. When they move faster, they will collide more the number of times. Na? The molecules, when they are moving faster, they will collide more number of times the walls of container. So this molecule will collide the walls. This molecule will collide the walls. So like this, all the molecules of the ideal gas will move faster than real gas and exert more pressure, remember. And here now, if you take real gases, between the gas molecules, there are attractive forces. Attractive force is there here. When attractive force is there, one molecule will be attracting what? The other molecule. One molecule is attracting what? The other molecule. When one molecule is pulling the other molecule, this molecule moves what now? Somewhat slowly. Somewhat slowly. So it will be moving very slow. The gas molecule of real gas will be moving slower than the gas molecules of ideal gas. Why? In real gases, between the gas molecules, attractive forces are there. We have to consider attractive forces. Then one gas molecule will be pulling the other gas molecule. Then the gas molecules will be moving somewhat slower than ideal gas. That's why number of collisions on the walls of container will be less. When number of collisions on the walls of container less pressure will be exerted. Less pressure will be exerted. Like this, what now? They exert what? Real gases exert what? They exert less pressure, low pressure. Then what? Low pressure, then what? Ideal gases. Ideal gas. So here we have taken 1 mole real gas. Here we have taken 1 mole ideal gas. Here V liters we have taken. Here also V liters we have taken. So same moles we have taken, but where it is exerting more number of more pressure here in case of ideal gas. Why it is so? In ideal gas, there are no attractive forces between the gas molecules. Therefore, more pressure will be exerted relatively. I think the point is clear to you. So that is called what? Pressure correction. So the pressure correction we have to make when you explain the real gases. Okay, we have to use what now? Pressure correction. So that's what he did. So the Van der Waals has introduced what? Pressure correction and also volume correction. Now, according to what your KMT, the gas molecule is negligible. So in case of ideal gases, in case of ideal gas, the molecule, this is molecule volume. Volume of molecule, that is what now here? 4 by 3 pi r cube. This 4 by 3 pi r cube volume is neglected here. It is negligible. It is negligible according to what? KMT. The volume of gas molecule should be neglected. Okay. Next here, in this case, the real gas molecule should be having some volume here. So the volume of molecule of real gas, the volume of gas molecule, that is 4 by 3. Anyhow, it is also sphere, na? Real gas molecule is sphere. Ideal gas molecule also sphere. Sphere means always volume what? 4 by 3 pi r cube. Therefore, volume of real gas molecule also 4 by 3 pi r cube only. But this volume of gas molecule should not be neglected. It should not be neglected. Is that clear, ma? So it is what now here? Should not be neglected. Cannot be neglected. So what cannot be neglected here? The gas molecule volume, real gas molecule volume cannot be neglected. That point we have to keep in mind. Okay, so that's why volume correction is to be introduced and pressure correction is to be introduced. To explain what now? Real gases. That point we have to understand here. So overall, what we have to understand now concept, Van der Waals has introduced what? Two corrections, volume correction and pressure correction. Next. So Van der Waals equation is obeyed, is followed by what? The real gases or wide range of temperatures and pressures. Or wide range of temperatures and pressures, the real gases obey which equation? Van der Waals equation. But ideal gases obey which equation? Ideal gas equation. Okay, so ideal gas equation was modified by Van der Waals, and he gave what? Van der Waals equation for real gases. Okay, so hence it is called equation of state for the real gases. It means what? Your Van der Waals equation. So this Van der Waals equation is called what? Equation of state for which gases? The real gases. Next, the Van der Waals equation for n number of moles. N number of moles of the gas is that. So number of moles, how many we have taken? N moles we have taken. So here P, generally what is ideal gas equation? Tell me. Ideal gas equation is what now? PV is equal to nRT. Right now. So in place of P, what we have to know? P plus AN square by V square. P plus AN square by V square. This AN square by V square is which correction, ma? Pressure correction. He has introduced it. And instead of V, what we are writing here? V minus NB. V minus NB. That means he has subtracted volume correction. The volume correction is subtracted from the volume. And the pressure correction is added to pressure. Okay, that means ideal gas pressure is there now. So in case of ideal gas, pressure we have taken and attractive forces we neglected now in ideal gas. That's why this is not there. But in real gases, attractive force is there. Attractive force is there. When attractive force is there, what we have to do? We have to add this pressure correction here. So he added what? Van der Waals has added pressure correction to the P, and also he subtracted volume correction from the V. Is that clear, man? So this point keep in mind. And here nRT, right hand side remains same, nRT. Okay. So left hand side of the ideal gas equation has been modified into P plus AN square by V square into V minus into V minus NV. So P plus AN square by V square times V minus NV is equal to nRT. So what is here? Pressure correction for molecular attraction. As molecular attraction is there in real gases. Molecular attraction is there in which gases? In Real gases. In real gases, molecular attractions there. So for these molecular attractions, we have introduced what now? Pressure correction and volume correction. Volume correction for the finite size of molecules, means definite size of the molecules. For definite size of gas molecule, we have taken what? Some volume correction. Okay, some volume correction is taken here. Is that clear, ma? So volume correction, this is volume correction, and this is what now? Pressure correction. So pressure correction is added to the given pressure, and volume correction is subtracted from the V. Okay, so that point we have to get. That means what now? Why we subtracted here? The volume available for the gas molecules is somewhat lesser than what? V of ideal gas. Than V of ideal gas. Suppose V is ideal gas volume, V minus NB is what? Real gas volume, which is somewhat lesser. The real gas volume available for compression is less. The gas molecules have less space in real gas for compression. But in ideal gas, the gas molecules have more space for the compression. That's why we have subtracted what? Volume correction from the V. And we added what? Pressure correction to P. Okay, that is equal to nRT. So equation once again read this one. P plus AN square by V square into V minus NB is equal to nRT. T is Kelvin temperature, R is universal gas constant, N is number of moles. Here N is number of moles. B is some van der Waals constant. V is volume. A is what again? Van der Waals constant. N is number of moles. V is volume. P is pressure. So A and B are what now? Van der Waals constants or Van der Waals parameters. Van der Waals parameters, otherwise Van der Waals constants. Okay. A and B, small a always you keep within inverted commas. Small a and small b are Van der Waals constants or Van der Waals parameters. Parameters. So parameters or constants whose values, A and B values, depend on the nature of the gas. So A and B values will depend on what? Nature of gas. That means what now here? A and B values of different gases will be different. Okay, for different gases, different values of A and B will be there. Normally, for a gas, A is greater than what? B. Generally, the value of A will be greater than, very greater than B value. For a given gas, for a particular gas, A value will be some very greater than what? B. That means you take CO2 gas, suppose. For CO2 gas, value of A will be very larger than value of B. Okay, ma? So A and B values depend on what? Nature of the gas. That means A and B values will be different for different gases. But capital R is what? Capital R is what? Independent of gases, na? Capital R is independent of nature of gases. Capital R is independent of what? Independent of nature of gases. That means what now here? On the nature of gas, R value does not depend. For all gases, R value will be same. But A and B values will be depending on nature of gas, meaning what? A and B will be different for different gases. But for a given particular gas, which value will be greater than which one? A value will be very greater than B value. That point keep in mind. Next, constant A. Information about constant A. A is what now? Van der Waals parameter. And it is indirect measure of, it is an indirect measure. It is an indirect measure of what now here? Magnitude of attractive forces. A, it means what? A is an indirect measure of magnitude of attractive forces. Whenever you see A, we have to understand what? Magnitude of attractive force. For a particular gas, A value is greater than another gas, meaning what? If A value is more, what does it mean? The attractive forces will be more between the gas molecules. If a particular gas has more value of A, what does it mean? In that gas molecule, the attractive forces will be greater between the gas molecules. So A is the measure of what? A is the indirect measure of magnitude of attractive forces between the gas molecules. That point keep in mind. Next, greater is the value of A, more easily the gas can be liquefied. more easily the gas can be liquefied. Means one gas is having greater value of A indicates that the attractive forces between the molecules will be greater. When attractive forces between the gas molecules is greater, when you compress that gas, the gas molecules will come close to each other, and due to more attractive forces, the gas can be converted easily into what? Liquid. Okay. So if value of A is greater, so greater the value of greater the value of what? A, greater the value of A, what we have to understand here, greater the value of A, more, okay, attractive forces, more attractive forces. When more attractive forces are there, what we have to understand, easily liquefied. The gas can be easily liquefiable, and the gas can be easily liquefied. So easily liquefiable gases will have greater attractions. Greater attractive forces are due to greater value of A. So greater the value of A, more attractive forces between the gas molecules, and hence the gas can be easily liquefied. That point mainly keep. Okay, thus easily liquefiable gases. Easily liquefiable gases like what? Sulfur dioxide, ammonia, hydrogen sulfide, carbon dioxide. Among these, already given here, which is easily liquefiable? SO2. Why SO2 gas can be liquefied easily? Because of greater value of A. So greater A value, greater A value, therefore what now? Easily liquefied. Therefore, this gas can be easily liquefied. So SO2 gas can be easily liquefied than ammonia. If you compress SO2 gas and ammonia gas, if you apply pressure on SO2 gas and ammonia gas, which gas can be first liquefied? SO2 can be first liquefied because it is having greater value of A. If value of A is greater, what does it mean? Attractive forces are greater in between SO2 molecules. Therefore, that can be easily liquefied. Is that clear, ma'am? So these points mainly we have to understand here. Is that clear? Next. So it's about what now here, the concept we have to understand about different types of gases. So these all among these four gases, SO2 has greater value. Greater value of what now? Greater value of what? Greater value of A, and hence volume will be greater. Next. So thus easily liquefiable gases like these gases have higher values of what? Higher values of A than the permanent gases like what? Nitrogen gas, oxygen gas, hydrogen gas, helium gas. Why these gases are called permanent gases here? Why they are mentioned about permanent gases here? Mostly these gases will try to be in gaseous state. These gases will try to be in which state? Permanently. They want to be in gaseous state. That's why they are called permanent gases. But actually, these two gases can be somewhat liquefied. These nitrogen gas and oxygen gas can be liquefied, but hydrogen and helium cannot be liquefied. Hydrogen and helium cannot be liquefied. Why they cannot be liquefied here? Because they have very less values of A. The values of A will be very less. For hydrogen and helium, very less A values. The values of A will be very less for what? Hydrogen gas and helium gas. That is why the attractive force between hydrogen molecules will be negligible. The attractive forces between helium gas molecules will be negligible. When attractive forces are negligible between gas molecules, they cannot be converted into liquid state. Okay, like that what now here, very less values of A will be there. That's why very less magnitude of attractive forces in hydrogen and helium. Therefore, hydrogen helium cannot be easily liquefied. That's why it is difficult to convert the hydrogen gas into what? Hydrogen liquid. Helium gas into helium liquid. So they try to be present in the form of what? Gases. That's why they are mentioned as what? Permanent gases. But among these four gases again, which can be somewhat easily liquefied, Nitrogen gas and oxygen gas can be somewhat easily liquid than what hydrogen and helium. Is that clear, ma? So it's about what now here? Constant A. Then units of A are as follows. Now here, atmosphere, liter square, mole inverse. First you take pressure correction. What is pressure correction? In the previous formula of ideal gas equation, what we have written pressure correction? A n square by V square. We added this pressure correction to what? P, na? So pressure correction is equal to what? P into A n square, A into n square by V square. So from this A is equal to what? Tell me now. A is equal to this. A is equal to P into V square, P into V square by n square, right? And now tell me here, what is P here? Pressure. Pressure means what now? Units will be ATM. V square means liter square by mole square. By mole square means what now? Mole inverse. Mole inverse. As is for now here, ATM liter square mole inverse will be the units of what? A. So units of A will be ATM liter square per mole square. Okay, otherwise ATM, okay, meter power 6. Why? 1 liter is equal to what? 1 liter is equal to, in place of liter, what we write generally, 1 meter cube is equal to, okay, meter into meter, right? So 10 power 2 centimeters, 10 power 2 centimeters into 10 power 2 centimeters. That equals to 10 power 6 centimeter cube, means cc. Cc means what now here? ml. Cc means what? ml. So now here 10 power 6 ml. Is that clear, ma? So in this case now here, what we have to understand here, 10 power 6 ml, 10 power 6 ml means how much here? 1 meter cube is equal to 10 power 6 ml means how many liters here? 10 power 3 liters. 10 power 3 liters it is. So 10 power 3 liters equals to 1 meter cube. Na? Okay. Then 1 liter is equal to what? 1 liter is equal to 10 power minus 3 meter cube. 1 liter is equal to what? 10 power minus 3 meter cube. So liter square means what therefore? Therefore liter square is equal to what now? Square of the liter, 10 power minus 3 whole square. So 10 power minus 6. Okay. So meter cube. Is that good? Meter power 6. So what here? 10 power minus 6 meter power 6 we have to in place of liter square. So in place of liter square, what we have to mention now here? 10 power minus 6. 10 power minus 6. What we have to take here? This one. So it is not written here clearly. So this one don't take here. So here in place of ATM, what ma? In place of ATM only. In place of liter square, what we have to write? 10 power minus 6 meter power 6. Okay. Into again mole square, mole inverse to only. So what we have to write? Tell me here. This one. ATM into liter square means what now here? 1 liter means 10 power minus 3 meter cube. Na? So here it is 10 power minus 6 meter power 6 into mole inverse 2. So mainly remember this one. This one is important. This unit is important for units of heat. Next, the same thing we can take in newtons. Newton meter to the power of 4 per mole square. Okay, so these are all conversions only. These are all conversions. We have to convert all these things. One units into another units here. That means what in newtons we have taken here. Okay, so these are all